Hello everyone, I am Dr. Naresh Kumar, Assistant Professor in the Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to have a discussion on classification of circuit elements. So first here elements are classified as the circuit element behavior, the ability of circuit. So now here elements are classified active elements and passive elements, linear elements and non-linear elements, unilateral elements and bilateral elements, time variant elements and time invariant elements, lumped elements and distributed elements. So first I will explain active and passive elements classification. So now here this one, active elements first. Elements are classified into two types, active elements and passive elements. Active elements means which are delivering the power to the other elements in a network, and passive elements are elements which are receiving the power from the other elements in a network. So always power flows from active elements to the passive elements. So now here active elements again classified into two types. So dependent sources and independent sources. These are two types, dependent sources and independent sources. Now here independent sources again classified into two types, voltage sources and current sources. Voltage sources are again two types, ideal voltage source and ideal current source. And next, current sources are again classified into two types, ideal current source and practical current source. Now here dependent sources are divided into four types. So now here dependent sources are divided into four types, means here four types: voltage dependent voltage source VDVS, or we can call it as voltage controlled voltage source VCVS, and current dependent current source or current controlled voltage source CCVS or CDVS, and voltage dependent current source and current dependent current source. These two are current source and these two are voltage sources. Now what about the passive elements here? Passive elements examples are resistors, inductors and capacitors. Now this is the flow chart for circuit elements according to the elements behavior: active elements, passive elements, the independent sources, dependent sources. In the independent sources, voltage source and current source, and in this again ideal voltage source and practical voltage source. In the current source also ideal current source and practical current source. And the dependent source VDVS, VDCVS and VDCS and CDCS. And passive elements examples are resistors, inductors and capacitors. And now here first category is active elements. Active elements are which are always sources of energy. All sources are active elements, are element which delivers the energy to the other elements in a network, are called as the active elements, which are delivering the power to the other elements in a network. The element which can deliver the energy are known as the elements which are which delivers energy are called as the active elements. So now here, so active elements examples are voltage sources and current sources and batteries. So this is the voltage source and this one is a current source and this is a power cell, batteries. All are which are delivering the power, voltage, are known as the active element. Now here what about the passive element which are receiving the power? Elements which consumes the power, which absorbs the power and which stores the energy in the form of energy, which receives the power and which dissipates the power, or which stores the energy in the form of magnetic field, in the form of electrostatic field. Such type of elements are called as a passive elements. So here passive elements examples are resistors, inductors and capacitors. Now here if you see the diagram here, this is the one power cell, the one battery. So now this is active element and this is the bulb which receives the power. Power always flows from active elements to the passive element. So this is the passive element, this bulb. Passive elements examples are resistors, inductors and capacitors. Fan. So all are which are receiving the power element are known as the passive elements. Now here voltage by current. If you draw the graph between voltage across the element, and let me change the color over here. voltage across the element. So if that graph, if that graph slope, so V by I ratio is negative, means that is active elements. If you draw the voltage current characteristics, so that graph V by ratio, that ratio should be less than 0, means that is negative, means that is active element. If it is positive, means V by I means that is, if it is positive, means that is the passive element. So now here active elements again classified into active elements, again classified as a independent sources and dependent sources. And independent sources again divided into independent voltage sources and independent current sources. Now here independent voltage sources, independent source, what do you mean by independent source? Which maintains the constant value for any quantity, which is not affected by any other quantity, is known as a independent source. Now these are two types, independent voltage source and independent current source. Now here this one, independent voltage source, which maintains a constant voltage, that means fixed value, which is not affected by any other quantity. And independent current source, which maintains a current, that means fixed, not affected by any other quantity. Now here, each independent source is divided into ideal voltage, ideal source and practical source. Independent, this one is divided into ideal voltage source and practical voltage source, and this one is also ideal current source and practical current source. And next, here ideal source definition is here ideal. So these are the imaginary source, ideal voltage source and practical current source are the imaginary source, which gives the constant voltage or current to the circuit regardless of load current and load voltage. And these are the sources which don't have any internal resistance. For ideal voltage source, it is a internal resistance is 0, and practical current, ideal current source internal resistance is infinity. So now we will discuss each one in the next slide. So where it is impossible to build a source with 0 internal resistance. Such type of sources are practical sources, that are real sources, practical sources. Now here, ideal voltage source. So now here ideal voltage source means these are the imaginary electrical source which provides a constant voltage across its terminal irrespective of current through its terminal. So these ideal sources don't have any internal resistance. Ideal voltage source internal resistance is 0. So now here this is the ideal voltage source symbol. So this is a voltage source plus and minus, this is the symbol. So now here this, if you connect the load, current flows in this is the voltage source. Now here this voltage source value and this load voltage value is same, this one in case of. Now if you see the statement here, constant voltage across its terminals, constant voltage irrespective of load current, regardless of load current flows through the terminals. And this is the Vs and this one is the VL. If you draw the graph between, these are the characteristics and this one is the circuit. If you connect the load, then only current flows, that current is IL and that voltage is VL. So now here this one, practical voltage source, this ideal voltage source internal resistance is 0, this R internal is 0. So now here practical voltage source, so these are not possible. Real sources, real voltage sources means which are having some resistance in series with ideal voltage source. Such type of sources are known as a practical sources, real practical voltage sources which is having internal resistance, not 0. In this case, this value is 0. This R internal is 0. So now if you connect the load, current flows in this and this is the voltage VL. So now if you draw the graph characteristics VL and IL. This is for ideal, already we discussed. And practical case, there is a drop, so that is I square R drop. Because of this resistance, I square R drop. So the graph, the characteristics should be like this. This is for practical, and this is for ideal case. Now what about the current source? Here current source means ideal current source, those sources, imaginary electrical sources, and which provides the constant current. In the previous case, constant voltage. In ideal voltage source case, constant voltage, and its terminals irrespective of voltage appearing across its terminal. In the previous case, irrespective of load current. Here, irrespective of voltage appearing across its terminals. So these have infinite internal resistance, means R internal is infinity. In the previous case, R internal is 0. Now this is the current source, ideal current source symbol, and the ideal current source circuit. If you connect the load, current flows in this load. If it is a closed path, then only current. In this case, no load means no current, current is 0. If you connect the load, current flows in this, and this is the load voltage and load current. If you draw the load current versus load voltage, and this is the source voltage IS, so it maintains the constant current irrespective of load appearing, regardless of voltage appearing across its terminals. So the independent of this voltage, this is the characteristics diagram. Now it is having high RSH in parallel with ideal voltage source. So now here this is ideal current source, and this is the parallel resistance in parallel with this. In the previous case, voltage, ideal voltage source in series with resistance, but here high resistance in parallel with this ideal current source. This is ideal current source. Now connect the load and current flows in this. If you draw the graph between this IL and IVL and VL, this is not IL, VL. So now here in this case, this is for ideal case, this already we discussed, and this is the practical case, this is I square R, this is IS. So now these are active elements and passive elements. So now here dependent sources. Dependent sources means output value is not fixed. So that value is depending on other elements voltage and other elements current. So these voltage, whose output voltage or current, is not fixed. That value is depending on the voltage or current in the other part of the circuit is known as a dependent voltage source, or another name is a controlled source. So these are this symbol is diamond shape, but independent source symbol is always circle shape. So now here, when the strength of voltage across or current flowing changes in the source for any change is connected in the network called dependent source, another definition, and these are represented with a diamond shape. So these are represented with a diamond shape. And next thing here, these are classified as 4 types: voltage dependent voltage source, and next voltage dependent current source, and current dependent voltage source, and current dependent current source. 4 types. So each classification, first one is, now let us start with first classification, voltage dependent voltage source, VDVS. So now it produces the voltage, it produces the voltage as a function of voltage depending on the voltage elsewhere in a given circuit. So this is the symbol for voltage dependent voltage source, voltage dependent voltage source. This is the dependent value, and this is the voltage source. Plus minus indicates the voltage. You can represent inside the diamond also. Next, in the voltage dependent voltage source, the voltage is depending on the other branch voltage. And next, this one is the one circuit, and this is the voltage dependent voltage source. If you see the diagram here, this one, this VAB is directly proportional to the VCD. This VAB equals to K into VCD. This value is, this is plus minus indicates voltage source, and this value is not fixed. This value is depending on this voltage across this CD element. So now here V is equal to K into V value, VCD, voltage across this element voltage. So now it is not fixed value. Same way here, current dependent voltage source means, so that value, it produces the voltage value, means that is as a function of current, and elsewhere in a given circuit, this is the voltage source you can represent in this, and voltage dependent, current dependent voltage source. Now here current dependent voltage source means this voltage source value is depending on current of another branch current. Here this one plus and minus, but this value is depending on this current value, this element current value. In the previous case, that value is depending on the voltage, so this element voltage, this VCD, but here this element value is depending on the current. Now here VAB is directly proportional to this, VAB is directly proportional to this current, so VAB equals to R into ICD. And next thing here, voltage dependent current source, it produces the current as a function of voltage, but it is current source. The first one we discussed, but that is voltage source, but this is the current. Current source means arrow mark. In the previous case, that is voltage dependent voltage source means that is plus and minus inside. So the diamond inside the arrow mark, this is the current source, current dependent, voltage dependent current source. So this is depending on, this is, it produces the current. That means current source and as a function of voltage. So now here in this voltage dependent voltage dependent current source is depending on another branch voltage, and next thing here another branch voltage, this current value, this current IAB value is depending on another branch voltage. So now here IAB is directly proportional to VCD. IAB equals to eta into, this is the constant, and VCD. Next, current dependent current source, it produces a current as a function of current elsewhere in a given circuit. So now here this is current dependent current source. Here current dependent current source, in the source as a current, it produces the current as a function of current elsewhere in a given circuit. It produces the current as a function of current, and the current source value is depending on the another branch current. Same thing here, this value, this current source value is IAB value is depending on this this current only, current dependent current source here. And now here active elements, already we discussed. So same thing, independent sources, dependent sources, ideal sources, practical sources, ideal current source, practical current source, ideal voltage source, practical current source. Now here passive elements which are receiving the power from the other elements in a network and dissipates and stores the energy in the form of electrostatic field or electrostatic field or magnetic field. Such type of elements are classified as such type of elements are passive elements here. So now resistors, inductors and capacitors are examples. Are now here this is the active elements, passive elements circuit. Here now here first resistors. What do you mean by resistor? Resistor is a passive element which dissipates the energy in the form of heat, which receives the energy from the active elements and dissipates the energy in the form of heat. So now resistor is different and resistance is different. Resistance is a property of material which opposes the flow of current. This is the resistor, and this property of resistance, this material which opposes the flow of current here. So now here symbol for this one, this is the symbol. So resistor symbol, we know very well this symbol, and representation is R, capital R or small r, and units for resistance is ohms. You can represent in this way units, and resistor component, the real picture, it looks like this. So now here this, so it receives the energy from the active element and dissipates the energy power in the form of heat, means I square R losses in the form of heat when current flows through the resistor. And next, what about the formula here? This is the resistor definition. This is the resistor one conductor, and this is rho, and this conductor length, this is the cross sectional area, and this is the rho means resistivity. Now here this is the R equals to rho L by A. This is the formula, actual resistance formula, and we can measure the resistance value, voltage by the voltage across the resistance, and current that according to the Ohm's law. V by I means that is resistance, but we can measure the resistance value rho L by A. L is the R is the resistance of the wire, rho ohms, and resistivity of the material, that is ohm meter in the ohm meter. And next, the length of the wire conductor, that means in meters. And next, A is the cross sectional area of the wire conductor, so that is a meter square. So now this is the formula, R equals to rho L by A. We know very well this formula. And next thing here, these are the formulas. So now this is the parameter and this is the relation. According to the Ohm's law, Ohm's law is directly proportional to where voltage across any element is directly proportional to the current, and that voltage equals to V is equal to IR. V is directly proportional to the I, and next V is equal to IR. Here R is a proportionality constant. R is a proportionality constant, that equals rho L by A, and I equals to V by R. This is for voltage and this is the current. If you rewrite this equation, I equals to V by R, and power equation, this one equals to power equals to this one equals to this one. P equals to voltage into current, product of voltage and current, and V is equal to IR. This one, that means I square R. I equals V by R means that equals to V square by I, V square by R. So now here energy equals to integral of power. So power consumption per over a period of time. So that is energy is the integral of power, that is dt equals to P into T. So that means P means I into this one, and I square R, this one is, this is P, this is P, this is P. So power equals to integral of power means that is P into T. So now if you see the formulas here, voltage across any element is directly proportional to I. So now that is Ohm's law. Now here this is for V is equal to IR, I equals V by R, P equals to V into I square R, that equals V square by R. So energy equals integral of P dt. So now here this is the formula for energy, voltage, current, power and energy. And next thing here, inductor. Inductor is a passive element which receives the energy from the active element and which stores the energy in the form of magnetic field when current flows to the element. So now here inductor is different and inductance is different. Resistor is different and resistance is different. Inductance definition, it is a property of coil that causes an EMF to be generated by changes in the coil current flowing through. The symbol for inductance is, it is a coil. It is a coil. This is a symbol. So now here this is the symbol for inductor, and representation is L and units are henries here. So now henries. The real picture, it looks like this, inductance. And now here next case, inductor. So now this is the coil inductance. So inductance formula here. So L equals to phi into N by, so this is one coil having N number of turns, and if current flows in this, there is a flux according to the right hand thumb rule. So according to the right hand thumb rule, so hold the conductor in your right hand. So this current thumb direction indicates the current direction, and this curl finger direction indicates the flux direction. If current flows in this and flux setups, this is curl finger direction flux, and this is the inner core of the material. Here L equals to this phi into N divided by I. So now here L is the inductance in henries, and N is the number of turns, and M is phi is the magnetic flux, that is magnetic field in the Webers, and I is the current flowing to the coil. So now same thing here, the parameters and relation, Ohm's law for inductors, V is directly proportional to the di by dt. So now here rate of change of current here. Now here L is a proportionality constant, L equals to voltage equals to L equals to N into 5 by I. This is the formula. And next thing here V voltage formula, V equals L di by dt and I equals to 1 by L integral. If you rewrite this equation for current, or if you integrate it, and I equals to 1 by L integral of V dt, and power equals same thing. We know this very, power equals to product of voltage and current, and this voltage equals to this one equals to L di by dt into I, that means Li di by dt, and energy equals to half Li square. This formula is important. Energy stored in the inductor is half into Li square. I is the current flowing through the inductor and L is the inductance. And next, what about the capacitor? Capacitor is a passive element which receives the energy and which stores the energy in the form of electrostatic field, electric field, whenever current flows through the element. And next, capacitor is different and capacitance is different, and it is a property of material and its ability to store the charge in the form of charge when it is placed in an electrostatic field. When capacitor is placed in an electrostatic fields, it is having an ability to store the charge. So that property is known as a capacitance. Capacitance symbol is, it looks like this, two parallel plates. So now this one or this one. So this is not the capacitor. So this is two parallel plates. This length must be same. So if it is, one is bigger and another one is smaller, means that is voltage source, not the capacitor. So now here the representation is C and units are farads, and the formula here C by V, coulombs per volts, is known as a units, and units for this microfarads are farads, and capacitor component, the real picture, it looks like this. This one, capacitor. You might have seen this capacitor in the TV board. And next, this is the real picture. So now here capacitor formula, two plates, one plate A plate and B plates, two electrodes, and this is the dielectric material. The dielectric material permittivity is epsilon here, and this length is this distance is d between these two plates, first plate and second plate, displacement, and A is the surface area of plate, and this one, and epsilon is permittivity, and C is the capacitance. Now capacitance formula, epsilon A by D. So epsilon is these two plates, plate area is cross surface area is here A, and permittivity of these two between these two in this area is epsilon, and the distance between these two plates is here D. So the formula C equals epsilon A by D. So now here same thing here for resistor, inductor, here for capacitor, parameters and relation. Ohm's law, V is directly proportional to the integral of I dt. For resistor case, V is directly proportional to the I, and for inductor case, V is directly proportional to the di by dt. For capacitor case, V is directly proportional to the integral of I dt. So this is for directly proportional, derivative and integral of. And C here, C is the proportionality constant, C equals to epsilon A by D, this one. And next thing here, epsilon A by D, this one. And next here, if you rewrite this one, if you derive with respect to the T here, I equals to C dV by dt. So now here, what about the power? Power equals to V into I. So that equals to V into I, means V equals to here I. What about I equals to C dV by dt? So you can substitute this one, and now VC dV by dt. So CV dV by dt, and energy stored in the capacitor formula equals to 1 by 2 CV square. This one 1 by 2 CV square. This is the formula. So now Ohm's law is voltage is directly proportional to the integral of current that is dt, and V equals 1 by C integral of I dt, and current equals I equals to C dV by dt, and power equals to V into I VC dV by dt, and next CV dV by dt, and energy equals to of CV square. So now the summary here, this is the element, resistor, inductor and capacitor. V is directly proportional to the R, V is equal to IR, and V is directly proportional to di by dt, V equals L di by dt, and V is directly proportional to the integral of I dt, that equals 1 by C integral of I dt, and I equals V by R, I equals to 1 by L integral of V dt, and I equals to C dV by dt. So now you can write the power equations and energy equations. Power equations means here I square R and V square by R, and next V into I. Same thing here, V into I, and next thing L V dV, Li di by dt, and CV dV by dt. This is the formula. And what about the energy formula of Li square and of CV square and I square RT, or V square by R into T, and V into I into T, that is P into T. So we know these formulas. This is for voltage, this is for current, this is for power, and this is for energy. So now here another category here, this one, linear elements. So linear element means here the voltage current characteristics, that is straight line passing through the origin at all times. Now here voltage current characteristics, or in another way we can define this element here. So an element or a system to be linear, it obeys the additive or homogeneity property, that means superposition principle. For elements, it always proportional to the current. So current is always proportional to the voltage, which obeys the superposition principle, means additive and homogeneity property. So that if you draw the graph between, examples are all ohmic resistance conductors. So now if you draw the graph between voltage and current, so voltage and current, so that diagram should be, it must be straight line and passing through the origin. So it must be straight line and passing through the origin. So this is the one. It must be straight line and passing through the origin. So this point is in how we will determine whether it is linear element or non-linear element. That if you draw the graph between, if you draw the some one element, suppose resistance, so that voltage and current, voltage across the element and voltage across the current. So if you draw the graph between these two, voltage and current, and that characteristics must be straight line passing through the origin. So that should be passing through the origin, and that must be a straight line. If it is okay, that is a linear element. Otherwise, voltage is directly proportional to the current. So if it is V is directly proportional to the I, or I is directly proportional to the current, so which obeys the superposition principle. So now here non-linear element. So now here completely opposite, the voltage current characteristics, not a straight line and not passing through the origin at all time. So now here in another way we can define this non-linear element. An element or a system is said to be non-linear. It does not obey the principle of additive and homogeneity property. That means which does not obey the superposition principle. Non-linear element means which does not obey the Ohm's law. Examples are diodes, transistors, and FET elements. And here the first statement here, which is not a straight line. So straight line means, so this is the straight line but passing through the origin. So this is the non-linear element, not linear element. So what is the condition For linear element characteristics, that must be straight line and that must be passing through the origin, but it is passing through the origin but not is a straight line. So next case here, it is a straight line but not passing through the origin. But not passing through the origin means here this is not a linear element, non-linear element, this one. And next thing here, not passing through the origin, not a straight line. So these three characteristics elements are under the category of non-linear elements. So the best example for non-linear element is diode. So diode characteristics is, so here in the forward bias condition and in the reverse bias condition, the diode voltage current characteristics should be like this. For a transistor is also like this here. FET characteristics. So these are not straight lines and not passing through the origin at all the time. So the best examples are in resistors, diodes, transistors and FET elements. So now here, time variant and time invariant. So time variant, the element is said to be time variant whose voltage current characteristics changes with respect to the time. So this is because of aging effect. Aging effect means after 1 year. So suppose if you measure some value for any element, so after 1 year, so aging effect, so that value may changes. So which changes the value. So voltage current characteristics that are different. So now in another way we can, and another category is here time invariant. So now here the element is said to be time invariant. So voltage current characteristics do not changes with respect to the time. So now if you draw the, if I draw the, so now here this is the one at t equals to t1. At this time now I am measuring, I am drawing the voltage current characteristics. Now here this value changes after some time. So now that value is, this is t equals to t2. Same element but for different times the voltage current characteristics are different. So such type of characteristics, such type of elements are time invariant because of the aging effect. So now if it is not changes, such type of elements are known as the t equals to t1 equals after 1 year is also after 2 years. So aging effect is not effect on the elements. Such type of elements are time invariant elements. Next, unilateral and bilateral elements. So now bilateral element means the impedance offered by bilateral elements is same either the direction of current. So current flows in the both the direction. So impedance offered by such type of elements is same. So now here see the definition. Voltage current characteristics here, so of bilateral elements are symmetrical on the first quadrant and third quadrant and second quadrant and fourth quadrant. So now here the examples are resistors, inductors and capacitors. Now here in this, if you see the, so now here we have 4 quadrants. So first quadrant, this is first and this one is the second and this is the second and this is the third. So first quadrant mirror image, sorry, this is first, second, third and fourth. Let me change the color over here. This is first, second, third, fourth. First quadrant mirror images, third and second quadrant mirror images fourth. So the first quadrant image and third quadrant image must be same, or second quadrant image and fourth quadrant image is must be same if you draw the graph between voltage and current characteristics. So such type of elements are known as the bilateral element. Fold, if it is a paper, so hold and draw the graph. If you fold the paper and fold like this and fold like this, so the both graphs should be coincide for that case. And such type of elements offer same impedance. And next thing here, this is the bilateral element. First quadrant image and second quadrant image is same. And next thing here, first quadrant image and second quadrant image same. Fold like this and like this, that image should be same. And next thing here, this one is also this one. So first quadrant image, let me change the color over here. So first quadrant image and third quadrant image same. First quadrant image, second quadrant image same. And second or fourth quadrant image, if it is graph should be like this also, it will be satisfies. And next thing, this is also satisfies, and this one is also satisfies, and this one is also satisfies. All these characteristics elements are under the category of bilateral elements. And unilateral elements means which offers different impedances, means current flowing in only one direction, which offers high impedance when current flows in one direction and low direction. So first quadrant image and second quadrant, third quadrant image and second and fourth quadrant images are not same. So now here, this is the diagram. Here, this is first and fourth first quadrant and fourth quadrant image is same, but it is not bilateral element, it is unilateral element, not same. First and third must be same. So this is not first and second is same, not first and third, or second and fourth should be same. And this is the diagram. Second and fourth is same, second and third is same, not fourth. Second and fourth must be same. So this is the, so for any graph, so that first and third graph should be same and second and fourth graph should be same. If it is same, that is bilateral element. If it is not same, that is a unilateral element. And in the unilateral element, current flows in one direction. In the bilateral element, it will offer only both the direction. So examples are diodes. Lumped elements means when the physical size of element is small with respect of all the signal wavelength, called lumped elements. So these elements are pure and physically separable. So pure resistors, inductors and capacitors are the examples for lumped elements. And when distributed elements means physical size is large size and single and distributed element, these are pure and physically separable, not pure and not physically separable instead of distributed. And the best examples for distributed elements are here. Distributed elements are transmission lines. I hope all these concepts are clear to you. If you still have any doubts in this lecture, you can comment in the comment section below. I will answer to your queries. Thank you very much to you all.
Like, share and subscribe. Hit the bell icon for more updates.